This is Lecture 2 in Module 3 in the book Problem Solving Guide for Mechanics and Thermodynamics, the force of friction. In Lecture 1, we work with the following forces: gravity, the normal force, which is a contact force, tensions in ropes, cables, strings, the frictional force, and air drag. The frictional force is by far the most complicated. There are two types of frictional forces: kinetic friction and static friction. Kinetic friction is when the two surfaces are sliding along one another. Heat is being generated. There's grinding going on. Static friction applies when the surfaces are not sliding along one another. For example, you park your car on a hill, maybe 5 degrees, and it sits there. Hopefully, it's in park. The emergency brake's on, the car's not moving. What force is preventing it from sliding down the hill? And the answer is the static frictional force between the tires and the road. Also, if the car is accelerating where the tires are not slipping along the surface, that's static friction. If you lock the tires, slam on the brakes, and you don't have anti-lock brakes, and you're screeching the tires, that's kinetic friction. When you walk, the force that moves you forward is the static frictional force between your shoes and the surface. If there was no frictional force, so some really slippery ice, you could not walk forward because you can't push backward on the ground. The force of friction depends on two things: the slipperiness of the two surfaces and the force with which the surfaces are being pushed together. A measure of the slipperiness of the surface is called the coefficient of friction. You can look this up on a table: wood on aluminum, whatever. It'll give you the coefficients of friction. Also, it depends on the force with which the surfaces are being pushed together. This is the normal force or the contact force. The force of kinetic friction is mu kinetic N, the kinetic coefficient of friction times F sub n, which is the normal force. Characteristic of the two surfaces: how slippery are they, and the force with which the surfaces are being pushed together. When the surfaces are not sliding, the force of static friction is less than or equal to mu static F sub n. So let's go back to the car parked on the hill. You cannot determine the coefficient of static friction by calculating the frictional force because you don't know when it's going to go. The coefficient of static friction will tell you when it's going to break. So you'd have to tilt up the road until the car started sliding. And you say, all right, now I know what the coefficient of static friction is. If the car's parked on a 5-degree hill and it's not moving, you can calculate the frictional force on it, but you cannot calculate the coefficient of static friction. You don't know how slippy the road is yet. You have to break it. So the maximum possible static frictional force is mu static F sub n. So mu kinetic and mu static are the kinetic and static coefficients of friction, and for any two surfaces, mu static is bigger or equal to mu kinetic. So if you're making an emergency stop, you don't want to lock the tires. If you lock the tires, that's mu kinetic. If you don't, that's mu static. As long as the tires are rolling along the ground without slipping, the static frictional force applies. As soon as you lock the tires, then it's kinetic. This is the reason why we have anti-lock brakes, because the static coefficient of friction is bigger than the kinetic coefficient of friction. You don't want to lock the tires. So let's try to gain some insights into static and kinetic friction by considering the following very challenging problem. A 5-kilogram block rests upon a 2-kilogram slab, and the 2-kilogram slab rests upon a horizontal surface. There they are. Blocks on top of a slab, slabs on top of a surface. The coefficient of static friction between the 2-kilogram slab and the 500-gram block is 0.5. The coefficient of kinetic friction between the 2-kilogram slab and the 500-gram block is 0.35. That's this surface right here. The bottom surface, the coefficients of static and kinetic friction are 0.75 and 0.6, respectively. A rope pulls the 2-kilogram slab to the left. Part A. The slab and the block are moving to the left at a constant speed of 40 centimeters per second. What are the frictional forces between the block and the slab and the surface? part B. The 2 kilogram block and the slab are accelerating to the left at 2 meters per second squared and moving to the left at 40 centimeters per second. So they're going 40 centimeters per second, they're speeding up. What are the frictional forces between the block and the slab and between the slab and the surface? If you use your intuition here, you might get the wrong answer, so let's use physics. Let's start by drawing the force diagrams. 500 gram block first. What are the forces on the 500 gram block? The easy ones are gravity pulling down and the contact force pushing up. The 2 kilogram slab is pushing up on the 500 gram mass. And there's a frictional force maybe in there somewhere. Those are the two easy ones. They must be equal in magnitude and opposite in direction because there's no acceleration. 500 grams is half a kilogram. Half a kilogram by 10 newtons per kilogram is 5 newtons. So the gravitational force on the 500 gram block is 5 newtons. The normal force is 5 newtons. Which way is the frictional force acting on the 500 gram block? Is it that way, to the left? Is it to the right? Perhaps it is not obvious. Let's consider the net force on the 500 gram block. We know it's not accelerating in the vertical direction, obviously. So the gravitational force and the normal force must balance, and we already figured that out. They're both 5 newtons. But it is also not accelerating in the horizontal direction. The problem says, part A, constant speed of 40 centimeters per second. There can't be any frictional force on the 500 gram block. It's not accelerating. The force in the horizontal direction has to be 0. This is consistent with the inequality for the static frictional force. We know what the maximum is, mu static F sub n, is 2.5 newtons, and it's less than or equal to 2.5 newtons, and 0 is indeed less than 2.5 newtons, so we're okay. Unless you know that it's just about to slip, you shouldn't be using that equation for the maximum static frictional force. Now let's consider the 2 kilogram slab. There's the slab. What are the forces on the slab? We have gravity pulling down. The 500 gram block is pushing down, right there. The contact force from the surface upon which the 2 kilogram block rests, 2 kilogram slab rests, is pushing up. The rope is pulling to the left, and the frictional force to the right. The 5 forces must sum to 0 because the slab is not accelerating. This is part A. It's going 40 centimeters per second, constant speed. The contact force between the 2 kilogram slab and the surface must balance the 2 downward forces on it. The gravitational force on the slab itself and the gravitational force on the 500 gram block. Sum of the forces in the y direction is ma sub y, which is 0. Solving for the normal force, we get 20 newtons for the weight of the slab itself, 5 newtons for the contact force from the 500 gram block. That's a total of 25 newtons. We have the coefficient of kinetic friction. It's definitely sliding along the surface. The 2 kilogram slab is grinding along the surface. It's being pulled along the surface. That's kinetic. It's 0.6. It's given as 0.6. There's the normal force, the contact force between the two surfaces. 0.6 times 25 is 15. So now we have finished part A. There's no friction between the block and the slab. The force of friction between the slab and the surface is 15 newtons. Now on to part B, in which it's accelerating. We'll start with the 500 gram block. It's accelerating to the left at 2 meters per second every second. If it's accelerating that way, there must be a net force in that direction. What is it? What force is pulling the 500 gram block to the left? There's the force diagram. What's that horizontal force? You can pause and think about it if you're not sure. It's the frictional force between the block and the slab. If there was no friction and you pulled the slab would just slide right out from underneath the block, and then the block would fall straight down when the slab is out from underneath it. The frictional force is pulling it along. All we need now is ma for the 500 gram block because we know the horizontal force. It's the frictional force. The mass is a half a kilogram, and the acceleration is 2 meters per second every second. Those are given. Multiplying a half times 2, we get 1. The frictional force between the block and the slab is 1 Newton. That's the force needed to accelerate it. That's the static frictional force. Now we don't know, we can calculate what the maximum is, and we should. We can confirm that this force is less than the maximum. The static coefficient of friction between the slab and the block can supply this acceleration. The contact force between the 500-gram block and the slab is 5 newtons, which we calculated. The maximum static frictional force on the 500-gram block is thus mu static F sub n, which is 2.5 newtons. That's the maximum. So if we wanted to calculate how quickly the maximum acceleration of the 500-gram block, then we can use this. But here, all we're saying is we calculated it. It's 1. 1 is less than 2.5, so we know the 2-kilogram slab is still hanging on to the 500-gram block. 1 is less than 2.5. We're okay. The frictional force between the slab and the surface is still 15 newtons, the same as it was in Part A. The reason is because the coefficient of kinetic friction is the same and the normal force is the same. It's 0.6 for the coefficient of kinetic friction, and the normal force is still 25 newtons. So the frictional force between the slab and the surface is the same as it was in Part A, 15 newtons. Now let's tackle problem 321 in the textbook. If you get this, your reward is you can attempt problem 3-33. Allison is hauling a 600-pound Franklin stove. I put the mass in, the weight, in the bed of her pickup truck. She's going 25 meters per second in a straight line. The coefficient of static friction between the stove and the bed of the pickup is 0.65. The light turns yellow. She has to slow down. What's the minimum distance in which she can stop without the stove slipping along the bed of the truck? She doesn't want that stove to slip. What's her minimum stopping distance? Seems like a complicated problem, but the key here is to isolate that stove. That's all we care about. Forget about the truck, the tires, everything else. Isolate the stove. Picture a stove traveling horizontally at 25 meters per second. It's going along at a constant speed. Then it slows uniformly and stops. What force is stopping it? Why did that thing stop? Think about it. What stopped the Franklin stove? You can pause and think about it if you want. It's the frictional force between the bed of the truck and the stove. If there was no friction between the stove and the bed of the truck, if there was ice back there, for example, it would not accelerate. And it would continue horizontally at 25 meters per second. That's not accelerating. It continues in a straight line at constant speed. And then it smashes into the cab of the truck. Effectively, the truck is stopping underneath the stove. If there's no friction between the bed of the truck and the stove, the truck stops underneath it, stove keeps going, smashes into the cab. The force diagram for the stove, gravity, normal, frictional force, is what's slowing it down. When the car stops, the friction between the bed of the truck exerts a force backwards on the stove. Now it's straightforward. There's no acceleration in the vertical direction. The normal force balances the gravitational force. The gravitational force is mg. The normal force is mg. In the horizontal direction, we have the frictional force. And we want to stop the truck in the minimum distance. If you want to stop it in the minimum distance, we need the maximum possible frictional force. And the maximum possible frictional force is mu static F sub n. So we set the frictional force to the maximum possible. The static coefficient of friction is 0.65, and the normal force is mg. And this is ma, because there's only one force in the horizontal direction. It's the frictional force. 0.65 mg is equal to ma. So the acceleration is 6.5 meters per second squared. If she tries to stop faster than that, the bed of the truck cannot supply that frictional force. It's going to slip, it's going to be kinetic friction, and kinetic friction is less than static friction, so it's going to accelerate. We are not done yet because we need the distance. Problem asks for the minimum distance, not the acceleration. The distance it would take to stop a car from initial speed of 25 meters per second when slowing down at 6.5 meters per second each second. Let's take a shot. Slowing down at 6.5 meters per second every second, that's about 4 seconds, right? A little bit less than 4 seconds to stop. You're starting at 25, you're taking away 6.5 each second. The average speed over the stopping is 25. The average of 25 and 0, that's 12 and a half. 12 and a half times 4 is about 50, a little bit less than 50. Let's get it exactly. V final squared equals V initial squared plus 2AX. Starts at 25 meters per second, ends up at 0. Acceleration is negative 6.5 meters per second squared. We can solve for x. It's 625 over 13, which is 48.1. That's consistent with our estimation, so we're pretty happy. There's a lot going on in this problem, but if we say, what are the forces on the stove? Set F equals ma for the stove in the horizontal direction, set F equals ma for the stove in the vertical direction, and it's not that complicated. Let's make it simple. For more practice with the frictional forces, try problem 3 on both exam 1 and exam 2 on page 118 in the textbook. Get to work.